So that's joint work with Noam Nissan. Okay, so we will consider the econometric estimation task. So let's think about that we are looking at some empirical data, and we would like to use parameters that we can observe in this data in order to estimate parameters that we cannot observe in the data. In order to make this estimation, we must make assumptions about how these parameters are related, and these assumptions are given in the model that we use. So this econometric task is not just statistics, but it combines data with some modeling assumption. And the model here is crucial. The model is what allows us to get parameters that we cannot directly get from the input data. But on the other hand, the correctness of this whole estimation process strongly depends on the correctness of the models that we use. So it is very important how we choose this model. And in this talk, I'll focus on repeated auctions. The observational data is going to be a sequence of bids that were played in repeated auctions. And we would like to use these bids in order to estimate the private values of the bidders, the players in these auctions. And the question is, which model should we use? And the standard way to do that is to make the equilibrium assumption at the model, which means to assume that the game is in a stable state where all players are best responding to each other. But this we know that is a very strong assumption to make, and it may be hard to justify in many cases in reality, especially in more complex settings like in the repeated online auctions that we're going to talk about today, or when the players are human, are real people, because of bounded rationality or biases that we know that people have. But in a recent work from,
When you said Nash equilibrium, did you mean a Nash equilibrium in the stage game or the repeated game?
In the stage game, that's what they do. They assume that the system has stabilized. Yeah. And in a recent work from EC, that also won the best papers there, so Nekipelov, Silkanis, and Tados suggested to use much weaker assumption for this estimation task, which is based on the idea that players are using some learning strategies that minimize their regrets in the repeated game. So the assumption here is that in a sequence of auctions, players have low regret. And the regret is in respect to the best fixed bid that the players could play. And this is the definition. The regret of player I in a sequence of auctions that is given by a sequence of bid profiles BT is just the gap between the best utility that the player could get by playing the best fixed bid through all these auctions and his actual utility, what the player actually got in these auctions by playing as he did, by playing BIT in every auction T. And notice that this regret minimization assumption is strictly weaker than the standard equilibrium assumption. We know that if the players are in Nash equilibria, but also in correlated or cross-correlated equilibria, so players have low regret. And there are also many learning dynamics that guarantees that players will have low regret. And this is the regret minimization method. So what it does, it computes a value estimate for every bidder by considering a range of valuations that we think that a player may have. And for each possible value V in this range, it computes the regret for the player had his value been V for the actual sequence of bids that was played, and then sets the value estimate to be just the value that minimizes the regret for the player. And this method has significant advantages over methods that rely on the standard equilibrium assumption. Like we said, it makes weaker assumptions, allowing for Nash and to much more general than Nash. And players can use dynamic strategies, which may be more natural for repeated settings and the stable state of equilibrium. And it also measures the success for the players only in an aggregative sense, only on average over a sequence of auctions. So players, this may be more suitable for players who do not optimize perfectly in every stage. And the second important point is that notice that this method is general. It can be applied to any repeated game. In particular, it can be applied to any auction rule. So if we get a new auction, we don't need to solve for the specific equilibrium for that new auction. Instead, just the same procedure is going to work. And like we saw, so the method is really simple. It doesn't have many details. And in their EC paper, they applied the regret minimization to derive value estimates for bidders in Bing ads of Microsoft. And they said that the estimates that they got were relatively similar to those that they got using the equilibrium-based methods. However, they couldn't tell how good the estimates were because when they use real auction data, they don't know the real values of the players. So they couldn't make this sort of evaluation based on real auction data. And this is what we're going to do in this work. Here we use data from a previous experiment that we ran with people in laboratory in order to evaluate the regret minimization method. And we're also going to compare the regret minimization with the equilibrium-based methods. And in the experiment, people participated in simulations of auctions similar to the auctions that are also running on Bing. But this is a controlled experiment, so we control all the parameters, including the values of the players, so we can directly compare the estimates that we get with these true values and see how good the estimates are. All right, so I'll start with describing the experimental data that we're going to use, and we'll mention a few of the previous results that are related to the current modeling question. And then we will ask two questions. The first question is whether it seems to be correct that human bidders really minimize their regret in the repeated game. And the second question is, how good is a regret-based econometrics relative to the equilibrium-based methods? Okay, so in the experiment, people participated in auctions similar to the auctions that the large internet companies are using to sell the positions for advertising on the side of the search results or on a web page like in this picture. So the objects for sale here are these ad positions, and each position is associated with the different click-through rates, CTR, and they appear on the page in decreasing order of click-through rates. And the bidders are the advertisers, and we assume that each one earns some value per click and plays a bid per click. And in each experiment session, we had 5 participants who were the advertisers, and in the beginning of every session, each one of the players was randomly assigned a value per click from this set of game coins. So we had 5 types of players in terms of their value per click. And this value was a private information for every bidder. Only he knew his own value. And they competed in a stream of ad auctions for 25 minutes. We ran 1 auction per second. So overall, there were 1,500 auctions in a game. And each auction sold 5 ad positions in decreasing order of click-through rates with these values. So the value per click was constant through the whole game, and the click-through rates were also constant. And we compared 2 mechanisms. First, it was the GSP, Generalized Second Prize Auction, which is the auction mechanism that is usually used to sell these positions. But we know that the GSP is not truthful. So we compare it with the VCG auction, which is the auction mechanism that maximizes social welfare. And we know that it's truthful. Under the VCG, it is a dominant strategy for every player to bid his true value. So we have GSP versus VCG. The 2 auctions make the same allocation of positions allocate the positions by decreasing order of bids, but their pricing rules is different. And we also compared 2 value information structures. In the first, we call it the given value setting. We denote it by GV. And here we just explicitly told every bidder what was his value per click. And this is the usual way to implement private value settings in experiments. And the second setting, we call it the deduced values, denoted by DV. And here bidders were not provided with their valuations, but instead could only indirectly deduce their own value from the feedback that they got. I'll show in the next slide how it looked like. So overall, we had all 4 combinations of mechanisms and value information settings in a 2x2 between participant design. All right. And this is the user interface. So every player could modify his bid here whenever he wanted. And we ran an auction every second using the current set of the 5 bids. And we updated the payoff results for the player in his total balance. And players knew that in the end of the game, they will be paid according to their final balance in here. And in this section, players could see how much they got in the latest auction that was refreshed on their screen, including the payoff and the positions that they got in this auction instance, and also the full allocation of ad positions in this figure here, with the click-through rates just fixed on the left. And here there were just 3 graphs showing the bids, the payoffs, and the positions over time, what the player got until now. And also notice the players did not know the values of the other players or the bids the others made. And like in the real auctions, they could maybe learn about them from the allocation results. And we ran 24 such sessions. We had 5 bidders in each session. So overall, we had 120 participants. And we ran it with students in the Hebrew University in Israel. OK, so this is our experiment. So was it clear? Yeah. And now, and we're going to use the data from this experiment. Now, before we move on to the regret result, I wanted to mention a few of the previous results that can give us some context. So the first thing that I wanted to mention is we expected to see that bids will converge at some point, but we didn't see any convergence, and in fact, bid modification frequency increased with time. And in this graph, we see the average number of bid modifications made by a player over the 25-minute game in each of the 4 experimental conditions. So the bidding activity increased in all conditions, and in the last part of the game, every player changed his bid more than 6 times in a minute on average. So clearly, bids did not converge in our experiment. And the second important point is overbidding. We saw that almost 40% of the bids were above the bidder's value, were overbidding. And again, we see it in all 4 conditions and through the whole game. And in VCG, we expected the players will play the dominant strategy and bid their true value, but we found very low frequency of truthful bids, even in VCG given value condition. Here, players knew their own value, and we also advised them how it was their dominant strategy to bid their true value, but even here, only less than 20% of the bids were the true value. But still, when we look at the bottom line of the results, of the welfare and the revenue for the auctioneer, we see that they were consistent with the theory. And here on the left, so this is the welfare as percentages of the optimal welfare over time for the GSP and VCG. So you can see that for both auction rules, the welfare increased quite fast and was above 95% during most of the game. And the revenue for the auctioneer are similar or even higher from the theoretically expected revenue, which is this red line. So what we see here is that despite all these weird things that the bidders did, and despite the fact that we don't see any convergence to equilibrium, the auction was still able to use these bids that the bidders played to make the allocation correctly by the true value. So it seems that it should be possible to use these bids to learn from them what were the private values of the players. And this is what we're going to do now in the econometric estimation task we are considering here. All right, now back to the regret question. So the first question we ask is whether human bidders really minimize the regret. And we found that the answer to this question depended on the type of the players, which is, again, the value per click that we assigned to bidders. And here we see the momentary regret, which is the regret computed in each minute separately for the players. And over time, according to the 5 types of players. And we show the regret as percentages of the optimal outcome. And we call it the relative regret. So first, what we see here is that the regret levels decreased for all types of players. As we could expect, that players did learn and did do better as time progressed. But we also see how players of different types had different regret levels. We see that the lower types had higher regret, and that was consistent through the whole game. And on the right, this is the total regret, which we compute over the second half of the game, including 750 auctions, according to, again, the 5 types of players. So we see here that the higher type players seems to be consistent with the regret minimization assumption, seems to minimize the regret reasonably well, less than 6% for the highest type, 45. But the lower types have very high regret. The lowest type here have more than 50% regret. So we see here that only this type which is a random type, we assign it at random to the bidders, had a significant effect on how players succeeded in minimizing their regrets, how rational they played. So we say that the poor here acted irrationally. The poor, those with lower value per clicks, remained with high levels of regret, were irrational. And we were surprised at first to see that, but it's actually consistent with other irrational behaviors that we observed in the previous studies that were also correlated with the types, that the lower type players tended to overbid more often and tended to change their bids more frequently. And maybe it makes sense to see differences between types, because notice that when the low type players play rationally, so they tend to get the low positions, and then they are maybe losing according to other considerations that they may have, besides maximizing profits. And when they are trying to win the higher positions, those that are losing money and have higher regret. So maybe if we want to understand how players behave in these auctions, we need to use psychological explanations, maybe in terms of auction fever or some sort of agency illusion. Maybe players have different utility considerations than we would expect them to have. All right, and now to the regret-based econometrics. So I already presented the regret minimization method, but this is the actual procedures that we applied to our bidders. And it gets as input the actual bid sequence. We use the second half of the game, 750 auctions. And it also gets the utility functions for the players. So different auctions are just taken in these utility functions. And it outputs the value estimate for each bidder. And what it does is really simple. For each bidder, we just compute the regret for the bidder for different possible values, and then set the value to be the values that minimizes the regret. And these are the regret results for our bidders. And what we see here in each one of the graphs, this is the average regret as a function of the possible values. And this is for the lowest type 21, the higher 27, up to the highest type 45. And the different colors are just different experimental conditions. And you can see that the regret curves have a very clear minimal point, and the values that corresponds to this minimum is what the method selects as the estimate for the player. So, for example, if we look at type 33, you can see that the minimum is really obtained around where we would like it to be, around the true value 33. But for type 21, you can see that the minimum is obtained too high. We would like it to be here, but it seems that a method that relies on this minimal point is going to overestimate values of players of this type. Okay, and now we want to compare this regret minimization with methods that rely on the equilibrium assumption, but since GSP and VCG have different equilibria, the standard methods are different for these two auctions, so we will look at them separately, but we use just the same regret minimization method for both GSP and VCG. So let's start with the VCG auction. The VCG is a very simple case for standard econometrics, because here players should simply play their dominant strategy, should bid their true value. So the standard method would just be to take the average bid that the bidder played in a sequence of auctions as the estimate for his value in these auctions. So we just compare the regret minimization with the standard method of just taking the average bid. And we see that the regret minimization managed to give similar performance as the average bid. And here we see the estimation errors. This is over all 60 VCG bidders. So the total estimation error is almost the same, and the error distributed similarly for the two methods. And here we see the error according to the 5 types of players for the two methods. So let's first look at the blue columns, which are the errors using the regret minimization. And the error is consistent with what we just seen in the regret levels. We see here that the regret minimization had better performance on, estimated better the values for the higher type players. We saw that they succeeded in minimizing their regrets, but have very high error on the lower type players, who we found that remained with high levels of regrets. And the yellow columns show the error using the average bid, and we see the same pattern of error here for both methods. The error was negatively correlated with the type. And we found this comparison to be quite good, because the average bid is supposed to be a very strong prediction for the VCG, and we see here that the regret minimization, which makes weaker assumptions and is general for different auction rules, managed to give similar performance. And the GSP auction, this is more complicated for methods that rely on equilibrium, because here there are many equilibria and there is no dominant strategy, so it is less clear what should happen in this game maybe. And there are mainly two methods that were suggested in the literature for deriving estimates for bidders in GSP, and we use them to compare the regret minimization. The first method, we call it the VCG-like Nash equilibrium. And here, the estimation is based on the assumption that players reach a specific equilibrium of the static full information game of the GSP, which gives the VCG prices. And here we follow what Varian did. He actually applied it to real auctions from Google. And the second method is, we call it the best response. Here, the basic assumption is that players are best responding to the distribution that they experience. And here we follow Etienne and Capello from 2010. And we see, again, that the regret minimization gave similar performance as the other two equilibrium-based methods. And the error was even slightly lower. This is the error over all 60 GSP bidders, 25% for the regret minimization over all bidders. The second is the best response, and the third is the VCG-like Nash equilibrium. And looking according to the 5 types of players, we see the same pattern of error. The regret minimization, but also the other two methods, performed much better in estimating values for the higher type players, but had very high error on the lower type players. Again, we see a strong negative correlation between the error and the type. Okay, so we saw how it was possible to use a regret minimization to get value estimates for our players in GSP and VCG. And we saw that the weaker assumptions that this method makes were sufficient for deriving the value estimates that were at least as good as those that we got using the equilibrium-based methods. And we think that these weaker assumptions and the fact that this method is general for different auction rules can make it applicable in cases where standard methods are less applicable at. However, we also saw how all methods still make mistakes, and especially on the lower type players. So now we ask, how can we improve the estimates? And in the paper, we suggested a few possible improvement directions. First, we suggested that even if we just combine the methods, so because different methods have different sources for their mistakes, we get something by just combining them. And we see that on our VCG bidders and show how even if we just take the estimate that we got using the average bid and the estimate that we got using the regret minimization and average these two, we get a better estimate than using each one of the methods separately. So this is one thing, and very simple. And the second, we suggest that we should maybe unbias according to types, because we found this type-based bias, and we showed on our GSP bidders something like an upper bound, which is, you can think about it as the most we could get as if we understood this bias and could perfectly control according to that. And that has a potential to significantly reduce the error over the 3 methods that we used for the GSP. So it seems to be worthwhile trying to understand these biases and being able to control it, to fix the bias. And the third direction, here we also use differences between types, but here we consider the regret shape and say that because we see that the players seem to really minimize regret, but they do not do optimize perfectly. So instead of just taking the minimal point as a prediction for the value, we should take advantage of the entire regret curve and set the estimate, for example, for the weighted average of the valuations with weights that are proportionally decreasing in the regret. And we are currently continuing in this direction. It seems to be very promising. It significantly decreased the error, and we are working on it now in a separate work. Okay, now just to summarize. So we saw all econometric methods err on low-value bidders, but are pretty correct for higher-value bidders. And that the regret-based econometric method is at least as good as classical econometric methods, but it is widely applicable. And now we want to improve the estimates further. There is still a lot of work there. And maybe more interestingly, how well does the regret-based method work in other repeated game settings? And that's it.